Welcome to The Explainer. Today, we're tackling a literal gravity-defying problem. I want you to imagine a drone. You know, lightweight, nimble, maybe just a bit larger than something you'd pick up at a local electronics store. Now imagine strapping hundreds of pounds of cast iron gym weights to it and telling it to fly 5 miles. Sounds completely impossible, right? Well, that is exactly the physical limitation that the aerospace industry is trying to shatter right now. We're going to explore how a massive government challenge and a frankly fascinating digital cheat code are about to completely rewrite the rules of vertical flight. Okay, let's dive right into this. Here is our roadmap for today. We're starting with the heavy lift bottleneck, then we'll look at DARPA's extreme lift challenge, navigate the gauntlet, discuss the prototyping problem, dive deep into DBbun's synthetic solution, and finally wrap up with the future of aviation. Part 1. The heavy lift bottleneck and the limits of current drones. So to really appreciate the massive leap we are about to take, we first need to set a baseline for what unmanned aircraft systems can actually achieve right now. 1-to-1. Current multi-rotor drones are fantastic, right? They're simple, they're relatively affordable, they're easy to operate, but when it comes to raw strength, they hit this stubbornly frustrating physics problem that has just plagued engineers for years. Their payload-to-weight ratio typically maxes out at 1-to-1, sometimes even less. So practically speaking, a drone weighing 50 pounds generally cannot lift more than 50 pounds of cargo. It is a fundamental physical constraint, and it's holding back the entire industry. And this bottleneck largely exists because of VTO, vertical takeoff and landing. Generating vertical lift without forward momentum or a runway, that requires sheer brute force. That means heavy motors, heavy batteries, which instantly eats up your cargo capacity. Moving to Section 2, DARPA's Extreme Lift Challenge. Enter DARPA. The Defense Advanced Research Projects Agency doesn't really do incremental upgrades. They incentivize researchers to develop completely unexpected solutions to massive challenges. And to break the industry out of this 1-to-1 bottleneck, they've launched the DARPA Lift Challenge, which happens to be backed by a massive $6.5 million prize purse. Greater than 4x. We literally just talked about the 1-to-1 limit, and DARPA is now asking competitors to build a drone that can lift more than 4 times its own weight. It's absolute engineering whiplash. It's kind of like carrying 4 versions of yourself on your back and then trying to run a marathon. But that is the exact new standard in vertical lift performance that DARPA wants to set. Section 3. Navigating the gauntlet. Because, you can't just strap a rocket to a drone and call it a day. DARPA has set up a rigorous gauntlet of very specific constraints and rules that competitors have to face to prove their designs actually work. The real crux of this challenge is found in these brutal constraints. The aircraft itself, fully ready to fly, has to weigh under 55 pounds to comply with FAA regulations. Now, to even get a qualifying score, it has to lift a minimum of 110 pounds. But remember that 4x target we just talked about? To hit that, a 55-pound drone has to lift over 220 pounds. And we are not talking about simulated weight here. The payload consists of literal barbell standard cast iron Olympic gym plates. The drone has to hoist that cast iron up to 150-foot cruising altitude, all while being operated by a pilot with a commercial FAA Part 107 certification. And this brilliantly illustrates exactly where this gauntlet takes place, the National Museum of the U.S. Air Force in Dayton, Ohio. Competitors have to navigate these incredibly strict 100-foot wide digital geo-fenced flight lanes. They have to keep their massively overloaded drones perfectly within a narrow 60-foot green zone corridor. If they drift just a bit, they get a warning. If they hit the red zone, the run is terminated. And if they somehow reach the outer edge of the map, it triggers a mandatory emergency protocol, which literally includes hitting a kill switch to drop the drone straight out of the sky. Plus, it's not just a quick hover test. This is a severe test of endurance. The mission is a 5-nautical-mile circuit, so the drone has to take off, quickly climb to 150 feet, and fly 4 miles fully loaded with those cast iron plates. Then it has to return, perform this highly controlled drop of the payload into a tiny 5-foot radius circle, and then complete the final 1 mile completely unloaded before landing. Oh, and the whole shebang has to be done in under 30 minutes. Section 4, the prototyping problem, or as it's often called, the hardware trap. This brings us to a huge narrative pivot. How on earth do you build and test something this experimental? If you're a university team or a garage innovator, how do you iterate on a 50-pound aircraft carrying 200 pounds of iron without wasting millions of dollars every single time it crashes? This is the classic hardware trap. Physical prototyping for this specific challenge is just an absolute nightmare.
I mean, a crash isn't just a broken plastic propeller. It is hundreds of pounds of iron and spinning metal plummeting to the earth, totally destroying the airframe, frying the electronics, and completely wrecking your budget. It's incredibly expensive and dangerously slow. And that creates a massive, massive demand for a digital testing ground. Teams desperately need synthetic prototyping so they can rapidly iterate, have zero material costs when a design inevitably fails, and run extreme stress tests safely.
Which brings us to Section 5, DBun's synthetic solution, the digital twin cheat code. To actually help teams survive this, DARPA created a contributor portal so companies could offer resources. And looking through that portal, one contribution really stands out as a critical cheat code for solving this hardware trap, and that is DBbun LLC. Just listen to this quote straight from DBbun's entry in the portal. Their resources help teams rapidly explore, compare, and stress test hypothetical aircraft concepts before committing to hardware. That hits the nail on the head. That is exactly what we were just talking about. DBbun is providing these massive, fully synthetic VTOL design spaces and mission simulations that are specifically focused on those extreme greater than 4x payload ratios. Let's step through how this actually builds out an entirely different workflow for competitors. Instead of just guessing and building, teams use DBbun's datasets to, Step 1, generate synthetic VTOL designs. Step 2, run those designs through large-scale, digitally simulated 5-mile missions. Step 3, validate that the design can actually survive a 4x payload over that distance. And only then, at Step 4, do they actually go out and buy the aluminum and carbon fiber to build the physical hardware. They're iterating completely digitally before ever touching a piece of metal. And what makes this even more of a game changer is that DBbun is driving open source innovation here. They're making these synthetic datasets available on Hugging Face, and the source code is just sitting right there on GitHub. By opening up this digital twin technology, they're completely democratizing high-level aerospace tech. It ensures that all teams, whether you're a well-funded startup or just a brilliant inventor in a garage, can focus on shattering that heavy lift bottleneck right out of the gate without getting bogged down by software hurdles. Section 6, the future of aviation, beyond the challenge. Let's zoom back out to the macro view for a second. Why does solving this specific bottleneck in a geofenced field in Ohio actually matter for the rest of the world? Because proving that a drone can lift more than 4 times its weight, especially when it's accelerated globally by DBbun synthetic datasets, is going to revolutionize aviation, period. Think about military missions that need to rapidly move heavy gear into contested areas, or advanced infrastructure inspection, where drones need to carry incredibly heavy, specialized sensor arrays. Imagine the logistics of heavy package delivery right to your driveway. Or rapid disaster response, where a small, easily deployable drone can just airdrop hundreds of pounds of water and medical supplies directly into a strike zone. It completely changes the math on what these systems are capable of. By moving all that trial and error into the digital realm, we're rapidly accelerating physical reality. So I'll leave you with this. When synthetic simulations shatter the heavy lift bottleneck once and for all, what will drones carry next? Thank you so much for joining me for this explainer, and keep your eyes on the skies.